right, y'all, so we're in for another simple harmonic motion question here. This one, again, is completely different. We've done several different types of graphs, but this is the first one where we are going to be doing energy on the y-axis and time on the x-axis. We did displacement as time, velocity in time, and acceleration in time. We did energy and position, but this is the first time that we are going to be doing energy and time together. All right, so we're going to try to answer the questions here. This is the variation of gravitational potential energy over time. So I'm going to mark right now that this is the potential energy, gravitational potential energy over time. And it does, in part A, says what is the first time that the pendulum passes through the lowest point in the swing. Okay, so I know that this is for a pendulum. That then starts me thinking about some of the things that I might be able to use later. All right, now the first thing is, what is the first time the pendulum passes through the lowest point in the swing? So I'm thinking about a pendulum. A pendulum starts up high, and then it swings down, and then it goes up, and then it comes back down, right? Now the graph is potential energy. So when it's swinging, it goes from a high potential energy down to a low potential energy. So the place where the potential energy is lowest, that should be the lowest point of the spring. And so I'm going to say that that's right here at 0.2 seconds. And so I'm going to say the answer here is 0.2 seconds. When the potential energy is the lowest, my pendulum is at its lowest point. Therefore, it should be that time right there, 0.2 seconds. All right? The next question says, when is the first time that the pendulum's kinetic energy and potential energy are equal? Now, this is a little bit harder question. Now, there's a couple of ways to go about this. One is just to simply recognize that the potential energy is turning into kinetic energy. So when will the kinetic energy be equal to the potential? Well, it's when half of the potential energy has turned into kinetic energy, because then I have half as much potential and the kinetic has gone up half. And so recognizing that this right here is the maximum potential energy, that is 1, 2, 3, 4, 5. It looks like 5 big blocks there. So if I look at that right there, I can say, well, the half of the kinetic energy would be right here. And if you can't see those marks, you could take a ruler, you could measure it, and you could measure how far it was. And I could say, oh, that's 6 centimeters. So at 3 centimeters, that would be the middle, right? So the middle would be right here. And so then I would go down from that point of the graph. I'm going to try to go as vertical as I can there. And it looks like it's at approximately 0.1. All right? So 0.1 seconds. Now, the other way that you can do this is we can draw in the kinetic energy, right? You could always draw in the kinetic energy. We know that at this point, the potential energy is at a maximum. So that right there will be the total energy, right? Where potential is at a maximum, we know that kinetic at that point is 0. That's how I know for sure 100% that has to be total energy, right? Because when the pendulum is at its maximum and we have a maximum potential energy, it's at rest there because it swings up, it stops, and then it comes back down, and then it stops, and then it comes. So every time it's at that maximum displacement, the velocity is 0. And so therefore my kinetic energy is 0, and then I get this idea that wherever the potential energy is a maximum, that will be my total energy. Now, the same thing should be true in reverse, right? When the potential energy is at a minimum, the kinetic energy should be at a maximum, right? And so we can go back and forth with this graph just to show just like that. And so my kinetic energy graph should look something like this. This, something like that, and this isn't perfect. I like my first idea a little bit better because I'm not very good at drawing these trigonometric graphs, but you can see that at this point they are equal to each other, and if they're equal to each other there, that must be the point when they have the same kinetic energy. So therefore, we get the time there, which is approximately 0.1 seconds. All right? Now, the next thing we're looking for is the period of oscillation. Now, this is really tricky. Okay, I'm going to erase my velocity graph here because sometimes it gets a little bit confusing having two graphs on there. So I'm going to go ahead, I'm going to erase my velocity, my kinetic energy graph. We can always redraw it if we need to. Okay, so there we go. Now, this can be tricky because it looks like from the graph that the period is from here up to there, 0.4 seconds. Now that is the period of the mathematical sine curve or cosine curve or whatever it is, but that's not what the question's asking. The question is asking, what is the period of the oscillation? Now think about this. This is a pendulum. So we talked about at this point, it starts up at a maximum. So we're going to say it starts at a maximum over on this side. Then it swings down to where it has maximum kinetic energy, and then it swings up, and now it's over here. Has it completed an oscillation yet? No, it hasn't, right? It hasn't finished that oscillation. So we actually need to go back down to maximum kinetic energy again, and then swing up to the other side. That's where I've completed a complete cycle. Okay, with energy, you have to be really careful because the potential energy is at a max over here and also over there, but that's not a complete cycle. So therefore, it has completed a full cycle at this point, which is 0.8 seconds. So the period is 0.8. All right, that's how long it takes to go from one side over and then back to the other side again. We could do the same thing if it was kinetic energy, right? Kinetic energy will do the same thing. That's because energy is not a vector, and so you can't see the direction there. The direction doesn't show up, and so therefore we can't tell the difference between when the pendulum is up on the right-hand side and when the pendulum is up on the left-hand side, or vice versa. We can't even tell by looking at this. I'm just making stuff up, right? So therefore, be very careful when you're looking for the period, okay? Now, we do have one more question. The last question is on the graph. Sketch a second line representing the kinetic energy over time. Now, I did already do that, but we're going to go ahead and do it anyway. So when the potential energy is at a maximum, the kinetic has to be at a minimum, and so on and so forth. And so therefore, I do still have a lot of my points are left here. And so my final graph should look something like this. I'm feeling pretty good about that, actually. Oh, not that one. There we go. Something like that, and that should then be kinetic energy right there, and that then answers the question. I hope that was helpful. Come back sometime, look at some of the other graph videos with energy with simple harmonic motion, or any of the other ones I got around here, all right? We'll see you next time.